One more second, guys. I need to put the YouTube on mute, otherwise I'll start hearing myself back. Wonderful. Let me start a new page. Oh, why am I not seeing the new page thing here? Give me 1 second, guys. Add page. So we have two things, guys. So let me recapitulate what we did the last time. We learned about support vector machines. In support vector machines, we have, okay, guys, sorry to interrupt. I had a small announcement to make. This Sunday, we are going to have the seminar that I talked about the last, actually I was planning to have the last Sunday. It's going to be there with that person in India who's been doing a lot of grassroots engineering work, small innovations that will help the common masses and so forth. So that is for this Sunday. It will be at noon this Sunday. So what it means is that we'll have a quiz on Saturday, and we'll have our extra session that we do right after that, after the quiz session, right? So we'll put both of those sessions together so that on Sunday we just keep the seminar, just as a clarification. All right, so with those things, let's get started. Last time we talked about support vector machines. The support vector machines are actually very simple machine learning algorithm. It's an algorithm that's quite simple actually, and based on the notion of a kernel. Now, there are many kernel-based methods. If you look at the literature, this whole field of kernels, using kernel methods is pretty vast and pretty deep. They use it for a lot of things. So today we'll use it perhaps a little bit more. But broadly, it's used a lot. Support vector machine just happens to be the simplest and the first one of them. The basic idea in support vector machines is that we have the notion of support vectors. These are lighthouses, essentially. The idea is that throughout the data, you find some inliner points, some specific points which you can light up. And you can think of it as sort of lighting up those points, declaring them, or these are your support vectors, these are your lighthouses. Once you have discovered these lighthouses, their purpose is they help you draw a decision boundary, a nonlinear decision boundary. So how do you discover these lighthouses, these support vectors? The way you discover these support vectors is, the implicit idea is that you take data where the decision boundary is nonlinear or potentially nonlinear, and you project it into a higher dimensional space. The underlying belief is that in a higher dimensional space, every decision boundary, no matter how complex how complex it is as a hypersurface, there will be a higher, even higher dimension where, or sometimes you don't even have to go to a higher dimension. Sometimes you just need to go to another dimension, a space of the same dimension sometimes. And when you do go there, the problem simplifies itself. It becomes a linear problem. Once it becomes a linear problem, then everything that we learned about maximal margin hyperplane, the soft and the hard maximal margin hyperplane, comes in. It's a straight river. So the basic idea is you want to flow the widest river possible through that data set in the higher dimension, a straight river. When you project it down to that, in the original space, that straight river is obviously a very curved river, potentially. It need not be straight. Now, those points that are there in the river or on the banks of the river, those lighthouses, uh, you find those in the higher dimension space, and then you come back. When you come back, of course, those points, those lighthouses uh, will be sitting along the very nonlinear decision boundary in the original space. Going from one space to another to solve the problem is a classic mathematical concept. It is often used. And today I realized that there was a simple motivating example that I could have given, which I didn't give, to illustrate this point. And I'm going to start with that. So you see why it is true that in higher dimension, it gets, all things can be linearized. Now that's a good news. The bad news obviously sometimes can be, it's not really a bad news, but it is a fact that you might not be able to visualize the dimensions very easily. Sometimes these are infinite dimensional spaces. Okay? So, and that is a little bit hard to get your head around. How do you deal with, how do you imagine infinite dimensional spaces? For that matter, how do you even imagine a four-dimensional space, a five-dimensional space, or something? And the way, well, the joke is, the way you do that is, you think in terms of the basic 2 and 3 dimension that you can, but loudly you say, as you can see in n dimensions, or something like that. Because quite often your intuition carries forward. So long as you know the traps, places where the higher dimensions are radically different from the 3 dimension, and you understand those differences, in all other situations, quite often your basic intuition of 3 dimension does carry forward to higher dimension, even to infinite dimension spaces. Right? And this is what we do. Like I remember when I was learning general theory of relativity, and even the basic idea is that space-time already is four-dimensional. It gets a little bit hard to understand that. And then comes general relativity, which goes and bends the four dimensions into a fabric, which has all sorts of bumps. Now it is even harder to imagine, but what you do is you imagine in 2 and 3 dimensions, and from there, you carry the intuition forward to your higher dimension. That's how it is. And the same is true for string theory. String theory takes it even further to 10 plus 1 dimensions. We all carry our intuition in 3 dimensions, and then we go there and we sort of manage with that because we haven't evolved an ability as a um, to get intuition in high dimension. But usually that's not an abstraction. Now, I gave the example, if you remember, of a a curve which could be represented as a polynomial. And the moment you could represent it as a polynomial, those polynomial terms become the axes of the higher dimensional space. But sometimes you don't even have to go there. I want to give you an example, which is quite simple to illustrate the point that going to higher dimension can be, is not necessary. The higher dimension could be actually of the same dimension rather. So I'll take this example. Imagine, are you guys seeing my screen? Imagine that somebody gives you a unit disk. Inside the disk, let us say, guys, could you, one of you please confirm that
Yes, we can see the unit circle
Yeah.
just fine.
you can see the
Ah,
unit?
yes.
Okay, thank you. So suppose you have points like this. And this thing, usually in the classroom, it's so much more easy to illustrate. These are, let me call it the interior points on the disk. And then associated with it are some exterior points to whom, let us give another color. Oh, this is rather multicolored. All right, we'll go with it anyway. Then you have points which are outside it. The yellow points are outside it. And we can sort of generalize and extrapolate. But this is, if you remember, this was actually one of your labs in ML100. In fact, classifier 3 was this. And you might want to, it would be instructive if you revisit that and apply a SVM on it, support vector machine on it to solve it. because that problem is essentially tailor-made for a support vector machine. I'll post the solution with the support vector machine to it. Today, guys, remind me, I don't know how long we'll continue with the session, but I also want to get you started with something called automated machine learning. Just as a reminder, it's an off-topic thing. Let me introduce some noise points here. Points. Make it look more realistic. So assume the data is something like this. Are we together? And it's something like this. And some couple of points are outside too. So there we go. We have this data. What can you say about the decision boundary? You would agree that the decision boundary is quite manifest. It happens to be this thing. This is your decision boundary, isn't it? This is your decision boundary. Let me make it very, very clear. And oh, what just happened? There we go. So these are your decision boundary. Now, this is evidently nonlinear decision boundary, isn't it? So I'll just say nonlinear in the original space. This. Original. Would you agree? This is a R2 space. Let us say that this axis is X1 and this axis here is the X2 axis. It is that. Now, could you guys see an intuition of something that will make it linear? Right? When you look at a problem like this, you ask, okay, can I use logistic regression straight away? And the answer that comes to mind is perhaps not, because it's rather a curved decision boundary, it's a circular decision boundary. So actually, this is one of the interview questions I gave to data scientists, should they have the misfortune of being interviewed by me. So then now I'll tell you something very interesting. Suppose you go to a new space. Let me call it X prime is equal to X1 square, X1 prime, X2 prime is equal to X2 square, right? And see what happens. Let's see what would happen there in that particular space. So you realize what is the equation of a circle, guys? The equation of a circle
is x1 square plus x2 square equal to
yes,
radius square.
Excellent. Of the decision boundary, if you write the decision boundary as an equation, it would follow this constraint. It would follow the constraint that x1 square plus x2 square is equal to some value, r squared, right? This, let me just take this as r. It would be r squared, the radius squared. But when you go to coordinates like this, what does this equation become? If x1 square is x prime, it becomes x1 prime plus x2 prime is equal to some value r squared. So suppose the axis is x1 prime and the axis here is x2 prime. Do you see that, guys? So what will happen?
A line. It becomes a line.
The line. In fact, this is, if you go here, if this is r and here also r, it will actually be this.
Yeah.
This would be it, right? This is the equation for this is x1 prime plus x2 prime is equal to r squared, which essentially is the same equation. And so what you will end up with in the transformed space are things like this. All the blue points would be inside the decision boundary here in the inner triangle from the origin to this little triangle, and all the outer points will become like this. Are we together, guys? This.
It should be R squared, right? Yeah.
Yes, in fact, this is R squared. You mean the coordinate? You're right. You are absolutely right. That correction, thank you for pointing out. The correction is R squared. So does this make sense, guys? So do you notice that you actually went from here to here, one space to another space, not necessarily in a higher dimension. You were lucky enough to get it in the same dimension. Are we together? Right? You could, so that's the intuition that you can use to do that. Now, there is actually another way of looking at it. What you do is, suppose I created one more measure of it. The measure is, I looked for every point. This is two-dimensional, guys. This thing is two-dimensional. If I look at it in 3 dimensions, let me look at it here, 3 dimensions, and see what happens if the z, I create a x3 dimension, think of it as z rather. Actually, typically in school, we think of not x1, x2, x3, but xyz, we think of it as z. This thing, suppose I create a z3, by definition, it is x1 square plus x2 square. Let us see what it will look like. What it will look like is, it will look like a surface that goes through this. And so let me make it. Convince yourself that this is how the surface looks.
Parabolic.
Parabolic surface, isn't it? This equation. It's very easy to see if you just forget x2 and you just think in terms of intuition. If you want intuition, just think what does y or z is equal to. What does this equation y is equal to x squared look? It looks like this. Y is equal to x squared. That's the intuition. I just generalized it to 3 dimensions. Right. So this is it. Are we together? And if you look at this, you will realize that your blue points were actually on the surface here. It is on the outer surface here. Actually, this begins to look like solid, but isn't solid. Let me emphasize the fact that this is this. And all the yellow points, if you think about it, they will be again on this surface, this parabolic surface, but they will be up here. So guys, just you could do this in our in the physical classroom. We do that. You can take a page and you can just put points like this. Just draw it, color it in a piece of paper, the inside circle. And all you have to do is, if it is think of it as a rubber band page or sort of a sheet of rubber, and then imagine that you're deforming it into the shape. You would agree that you could do that. And this becomes this. And when it becomes this, where is the hyperplane that is the decision boundary? This is the hyperplane. Hang on, let me use a different color. This is the hyperplane. Let me use, well, I have used white. What can I use for the decision boundary? Blue is gone. Green. Let's go with
green.
Yes, let's go with green. You would agree that the decision boundary would be this plane that sort of cuts here. Do you see that? This plane that is cutting it right here. Imagine a horizontal plane. The green is a horizontal plane. Plane cutting at some place at z is equal to r squared here. Sorry, x3 is equal to r squared, if you think.
all the blue and yellow data points are on the surface of that three-dimensional parabolic object. They're not inside it. They're
No,
on
no,
the surface.
no, yeah. So yeah, they are on the surface of the parabolic object. Yes, that is true. And so in other words, that parabola is not solid. It's just a surface. The yellow points are above a certain threshold, above the plane, and the blue points are below the plane. Is that?
So it's almost like a telescope, as if like a telescope.
It sort of looks like a telescope or parabolic, the surface of a telescope, a radio telescope, parabolic, or something like that. Yes, it is like that. So guys, I hope you can see how you can take data. Do you notice that in this space, the decision boundary was circular? By going to a higher dimensional space, what have you done? You have lifted, you have created another dimension in which actually on X3, there is just a cutoff point. Above that, it is, so when you write an equation, X3 is equal to R squared, what is it? X3 is equal to some constant. So it means that's your decision boundary. All points above the plane on the parabolic surface will be yellow. All points below it will be blue. I don't know. Is this intuition clear, guys?
Yes.
So this is your main intuition of going to a higher dimension and solving it, and sometimes going to not necessarily higher dimension, but going to some other space and solving it. Or if you want to put it a little bit more poetically, you can say that for every data, there is a native space in which it's much easier to understand it. It's very simple. It simplifies itself. Okay, so that is that. So that's the intuition of the support vector machines. The job of vector machines is to discover these high dimensional space in a systematic way. But what is more interesting is you can say, all right, now it is complicated because I need to go from x1, x2 to this, find this complicated mapping that will go to some other higher dimensional space. Let me call this x1 prime, x2 prime, and x, let's say d prime, and you don't know what d is, first of all, and you don't know what the complicated rules of psi are. Actually, people use not psi, they use phi. Sorry, I apologize. Phi are, right? What that takes a point to a higher dimension? Yes, go ahead, please.
Asif, I'm just, it was a little difficult to grasp the three-dimensional thing. So for me, intuitively, it was a paper, and it's like a rubber platform. I folded it into a nice parabola.
Yes.
So x square plus x1 square plus y1 square equal to r square was the initial two-dimensional circle.
Yes.
So at a distance of r is from the center is where the separation boundary is, the decision boundary. But when you fold it up, you are still going up to r square or r. So that part I slightly couldn't understand. I know you're projecting it in the third dimension, but intuitively I was folding the paper up into a parabola, and then I have to go r square distance up in the x3 direction to hit the decision boundary. So that part I was a little.
So this parabola, very, very good question, actually. So this, let me out. So see this decision boundary that is here, this thick decision, its height everywhere, everywhere would be exactly r square.
Okay.
Now a plane, this line is sticking up exactly at the height of r squared.
Hey, Asif.
Yes.
Hey, will the height be r square, or from the origin to the point where the plane is cutting, that is r square?
Now think about this.
On the surface of the parabola.
Yeah. See every single point here, right? This point corresponds to the x3 value, right? We are
x3,
saying
okay.
x3 is r squared, which means that x3, this plane, what does this plane represent? This plane represents x3 is equal to r squared, a constant, right? So just think about this. It's a horizontal plane, isn't it?
Yeah.
On this horizontal
Okay.
plane, every single point is at the same height from the ground.
Right.
Of the ground made up of x1 and x2, isn't it? And so all the points on the parabola, the decision boundary points, wherever this plane cuts the parabola, the whole decision boundary is at height r squared, because every point on this plane is at a height of r squared. Right, r squared. Are we making sense?
I was just thinking, definitely they are of constant height, but will that be r square? That's what I was thinking.
It is, no, because this is literally the definition of this x3, the way we have defined x3.
Or we have defined x3 like that. Okay.
Strictly like that. If you choose, you could define x3 square is equal to x1 and x2 square, because then it looks more sort of symmetric. But you don't need to. I mean, it doesn't matter. This is it. So the point is that your real boundary in higher. So now the intuition is, look at this. In higher dimension, I'll put it. In higher dimension, in higher R3 space, the decision boundary is the linear, if you look at x3 is equal to r squared plane. It is this plane, isn't it? And in this, in our R2 original space, is a circle, isn't it, guys? And you can literally see that happen. This plane is touching the hyperbola, or sort of parabola. I take this, but parabolic, well, not parabola, but parabolic surface at this circular place, isn't it, guys?
So I have questions, sir.
Yes.
So,
One second. Let me finish this argument. So this circle, when you project back into, you look at the projection back onto the two-dimensional surface, x1, x2, you can literally see a circle on the ground, right? This thing projecting down to a circle in the ground, right? Which is the original circle that we have. Go ahead, Sukhwal.
so sir, circle in 3 dimension, isn't it a sphere?
But we did not choose to lift it into a sphere. We did a very specific lift. You remember, x3 is x1 square plus x2 square. I didn't say that x3 squared is equal to that, right? That would have made it into a sphere.
Yeah, but in 3 dimension, our data distribution looks like a sphere. So I'm a little confused, like how?
It doesn't, Sukhwal. Think about it. See, here is the illusion. The height of a point in 3 dimension is is proportional to the square of its distance from the center, from the origin. Think this way.
Okay.
For every point, the x3 value, the lift, right, the going up in x3 is equal to the square of its distance from the distance from the origin, right? Distance from the center. So because it's a square, it will look like a quadratic surface.
So the distance, every point is x square plus y square plus g square.
No, it is not. It is not. We are not talking about that. Every point is given as, see, this is the square of the distance.
Sir.
The square of distance. And we are saying that the z-axis value, that x3 axis value, is simply the square of the distance. What we are not doing is x1 square plus x2 square plus x3 square is equal to some constant, because that would be all points on a sphere.
Yeah, that's surface area.
Yeah, that's right. And we are not doing that. we are declaring that the x3 value, the lift or the height of a point from the ground, is proportional to the square of its distance from the origin, right? So when
Got it, sir.
proportional to square, it looks like a curved surface, right? It looks
Then
like
it's curved, yeah. Yeah, then it's curved. So
a curve, yes.
so G height is x square plus y square.
Yes, exactly. The z height. And here I called z by x3, right?
Yes, sir.
And the basic intuition is, you look at this plane, decision boundary is very obvious. It is actually the hyperplane, it's just the plane, the horizontal plane, where x3 is equal to r squared, that certain height, distance from the decision boundary, right, from the origin, at a certain distance from the origin, is the plane. X3 is a plane. Is that obvious, Satpal? X3 is equal to r squared is a constant decision boundary. It is a flat surface in 3 dimensions. And therefore, the decision boundary is a linear decision boundary. That green surface that you see, the green
Yes, sir.
plane that you see is the decision boundary. But
Yeah.
when you come back and look, what does it look in 2 dimensions? In your 2 dimensions, it is basically the projection of the intersection of this plane with this a parabolic surface. And that is this circle. And when you project it down to the ground, it is still the circle, which is exactly the circle that you're looking at. So in other words, in 3 dimension is a green plane, in 2 dimension becomes this wide solid line. You see that, right? Is anyone else, are you guys getting the intuition? It's a simple geometric intuition, but it
So
takes
Asif, looking
Yes,
from
yeah,
top,
I'm getting
you
it.
just
That is
lift
good.
it in the height.
exactly. All you did is
You lift it all by that equation, x3 equal to x1 square by x1. You lift all the points up and then slice it by looking from bottom.
yes, you just literally put a horizontal slice. Imagine just taking a knife and going horizontally and cutting through this plane, isn't it?
Yeah, now I got it. Thank you.
Yes, it's a very simple and beautiful intuition. And this is the foundation of this idea, is the foundation of support vector machines. Now, this idea, intuition is great, but there is a further fact which makes it computationally possible, which is that there's a kernel trick. You will learn about the kernel trick in the math class when we get to that, because quite literally, it's about dot products and vector spaces and all of these optimizations, constraint optimizations. So this is literally what it is. But we'll leave that for the next class. But the basic intuition is you can do that with the kernel trick. What happens is you don't have to truly find this phi that you have. You don't have to find, because there is a trick. I won't write the equation. The dot product between x and, let me just say x and x, well, I used x prime for the different space. So let me just say that the dot product between 2 vectors, A and B, right? It has a certain relationship. If these things get transformed into the other space, we could say that there is a phi A, phi B, and let's say that this function is there. This can be computed, this kernel can be computed without necessarily very explicitly understanding what in the world is this phi in closed form. You don't have to do that. It's sort of the thing that makes this magic computationally possible. So that's a computational detail. Let's not get into that too much for the time being till we get to the math class. So I hope I summarized the concept of the kernels.
So Asif, what is the phi and the k here for this going from 2 to 3 dimensional? You did it manually, but
yes. So here, so in this particular example, let us say that I gave you 2 possible journeys, from here to here, and then from here to here. For this one, the phi of x. Actually, why don't I leave this as an exercise? Because this is actually one of your very, very basic exercise in the math. I don't want to give out the solution right away. I'll let you find out. How do you do this? Yeah. It's staying in the face, but I'll let you do that. It is, well, okay. It is literally x1 the vector spaces are x1. So suppose you have phi x1, x2 is literally x1 square, x2 square. A new point in a higher dimension. This is it, right? X2 square. The square of the points. And then likewise, this one is very simple. You have the new points are phi, new points of x1, x2 are this set. x1, x2, x3, where x3 has this relationship, the constraint equation, x3 is equal to r squared.
Thanks, Asif. I'm getting the hang of it.
And K is just the dot. I mean, in the simplest form, think of K as just a dot product, A dot B. Is the simplest kernel you can, the dot product, or in basic notation, A dot B. Think of it like that. In a simple example of a K could be, simple example, could just be a dot product. But actually, it could be any function of the dot product. Are we together? So, for example, in the polynomial kernel, it could be A dot B to the power, some polynomial power. In the case of a radial basis function, minus gamma A dot B. Right? So you notice that K's are, these kernels are just functions of the dot product. They're just functions of the dot product. That's all it is. There's nothing very magical about this. We use the word kernel. It's sort of the word used in the literature. We do that. So now I'll tell you about something very interesting. In the last ML100, we talked about dimensionality reduction. And we learned about a technique called PCA. Does anybody remember what PCA stands for?
Principal component analysis.
Principal component analysis. So without recapitulating the whole theory of it, let's just say that basic idea is, if you're looking in 2 dimensions, if your data has a direct linear correlation, there's a correlation or there's a linear relationship like this in some form, it could be in 2 dimensions or 3 dimensions or 4 dimensions. There is a ellipsoidal envelope you can wrap data. Basic intuition is you can shrink wrap the data in an ellipsoidal envelope. Isn't it? So here it is, the ellipsoidal is not actually necessarily 3 dimensions or 4 dimensions. It's very simply, this is the ellipse, isn't it, guys? It's a simple 2-dimensional ellipse.
Yeah.
Yes,
When
sir.
you can do that, an ellipse has the major and minor axes, the principal axes. This is one axis, this is another axis. Those axes, so then this major axis, let me just call this axis as U1, U2. Let me put unit vectors along that. So you will have directions U1, U2, etc. And then you will have a certain amount of stretch along those axes. And by the way, these axes are also, when we did the little bit more on the theory of it, these are also the eigenvectors of the covariance matrix, covariance matrix X1, X2, there's a matrix. So we won't do the whole thing, but just say that there's a bit of mathematics that says that if you take the matrix and you do something called an eigenvalue decomposition, then these are your eigenvectors. But forget the math. Just think about the intuition that you can shrink wrap it into an ellipsoid. It has unit vectors along the principal axes. Those are your principal components. And the degree that you stretch along each of these, the lambda 1, lambda 2, lambda 3, so forth, these are called the eigenvalues. And the beautiful thing is that they have an order. Lambda 1 is greater than equal to lambda 2 is greater than equal to lambda 3. It is like that. And not only is it like that, but it follows an interesting behavior. sort of a power law decay behavior, quite often you will notice that lambda 1, lambda 2, lambda 3, lambda 4, there will be lambda 1 will be pretty high, lambda 2 will be, let us say if you're lucky like this, lambda 3 will be let's say like this, lambda 4 will be like this. So what will happen is if you connect these lines, right, you notice that there is an elbow here. Right. So this is the value of lambda 1, 2, 3, 4, lambda 1, lambda 2 rather, value, the magnitude of it. So elbow point, and you basically say that if a situation is like that, I can keep only these three and throw away the rest of the components, right? Rest of the dimensions I can throw away, and I'll get a pretty good approximation of the data. Just like in this case, you could argue that you have, I can keep only one axis of the data, and for any point, I just forget about this perpendicular axes. I just tell where a point is along the main diagonal axis, and that is the coordinates in one dimension. And I don't care about its location along the other direction. You can sort of ignore it because it doesn't matter, or you don't lose much by that. To do so is to do the dimensionality reduction. So that was the intuition that we have. Guys, do you remember that all your videos are still there? If you go to the page that I created for ML100, I hope you all have the hyperlink to that page. So all those videos are there for you. You all have access to it. If you want to review it, please do go review that dimensionality reduction session. I think it was the last session that we did in the previous workshop. So now what does that have to do with kernels? So for example, what does that have to do with what do kernels have to do with dimensionality reduction? See, let us say that you're talking about a sort of a data which is on a surface, something like this. Now, how do I draw a three-dimensional surface or two-dimensional surface? Let us say that most of your data is along this surface, this curve. This is your data set 2. It is like this. If you go back and look at your, well, obviously I did not make it symmetric. So let me make it a little bit more symmetric. Not that it has to be symmetric, but okay. Data set 2 look like this. So I'll put it like this here. You remember this was your data set 2? From your ML100. So in the previous class, introductory class. So if you look at this curve, if you try to create a covariance matrix between x1 and x and y, a covariance of xy, you will get something approximately 0 actually. Correlation, the covariance would be 0 or the correlation would be 0. Why? Because the relationship is not linear. At some point, they seem to be positively correlated. At some point, they seem to be negatively correlated, and again, positively correlated. And the net effect is probably a 0 correlation. Guys, are we together? Is the intuition obvious? Right.
Okay.
So now the question is there a way to linearize this? Can we linearize it? This, linear.
Yes, sir.
This, so that this begins to look like our old problem of data along, let us say something like this. Can we convert it to, it doesn't matter what, oh, sorry, what did I just do? I apologize. I was up to something. Give me a second, guys. I might have closed accidentally the OneNote. Too many notes on the desk. Yeah, okay. Sorry. So is there a way, and it doesn't matter at what angle or tilt it is, but can we somehow convert it into a linear problem is the fundamental question. How can we go from here to here? You can say, well, that is very easy. We can apply a kernel trick. The kernel mapping. right? We know that there is a way to go to a higher dimension where all curves and surfaces get linearized, isn't it? But once it gets linearized, then the old technique of PCA comes in, isn't it, guys? You see the two-step process. We can still do dimensionality reduction on a nonlinear curve like this by first linearizing it and then applying our PCA to it. Let me write down the two steps. First, first, linearize the problem. This is terrible. Linearize the problem by going to a higher dimension, right? So x goes to some phi of x, right? Some this, and b then do the PCA, then do the regular PCA. What say you guys? Is this more straight? Is this obvious? This two-step process? I do some feedback, guys.
So why we are doing PCA once we linearize the data? Then
the whole point was that we need to do dimensionality reduction. We need to reduce it, let's say, to just here it is two-dimensional data. We want to reduce it to one-dimensional data.
Got it.
Right? Okay. So you realize that we are doing something very counterintuitive. We want to reduce the dimension, not increase it. But the way we do it is we first increase the dimensionality. We go to a higher dimensional space where the data is linearized, and from there we come down back to a much lower dimensional space, right? So you're effectively sort of going from 2 dimensions to 3, let's say 3. I'm just taking a hypothetical example. In this case of a sine wave, which is, let's say, a 5-dimensional space, a 5 dimensions and something, and then coming down to 1 dimension. But you, at the end of the day, you still have come to a lower dimension. The only dimension that will matter is that the straight line dimension, that is called kernel Pca. Right? That is the kernel Pca. Right? So you can generalize a lot of these linear methods using the kernel approach, applying this. People call it the kernel method often, that going to a higher dimension, solving it and coming back. Like the kernel trick is more widely applicable beyond just support vector machines. So there's a large body of literature on kernels. Kernels are still going very strong. They're in many, many areas of machine learning. So guys, before I move on from here, I would like to know, are we clear? Did we understand what we just did? We used the kernel to go to a higher dimension, which is linear. And from there, we actually found a shortcut to a much lower dimension, right? So it is almost opposite. Kernel takes you up, PCA brings you down, but the net result is down, lower dimension.
So the kernel we'd want to use in this example be like a sine wave, or?
Yes, it could be a sine wave kernel. You could use you could just custom make it, or you could use actually polynomial kernel would serve you better, because remember we did the 5th degree polynomial and that served us quite well in ML100.
Okay. So if the data distribution is like 3-dimension in kind of blob, or like, let's say, amoeba shaped in 3-dimension, is it possible to reduce the dimension in that thing?
The problem is mathematics is insanely powerful. So the idea is that, yes, you can do that. The question is, so there does exist some space where the problem is linearized. The question, with the kernels that you have implemented in code, see, the code doesn't, the libraries don't go and try every possible function mapping. They have just a few tricks up their sleeve. They will use a linear kernel, they will use a polynomial kernel, or they will use the exponential kernel, you know, the radial basis function kernel, the Gaussian kind of kernel, these 3 mappings that I mentioned. Where did I mention this? These 3 mappings, right? These typically are the ones that comes built in with most libraries. Now, libraries are extensible. So to Kate, your problem, could I have just used a sine wave kernel? By all means, but you have to plug it into the library. It gives you a way to plug in your custom kernel.
So Asif, can we use like a DB scan because it is like a different type of a non-globular structure?
No, that is for clustering, no? And I don't.
Oh, that is for clustering.
It doesn't have relevance here. Here we are doing dimensionality reduction.
So,
Asif?
sir, I'm sorry, Patrick. So I have actually a real data set, and it's a clustering problem, and we are trying to reduce the dimension by PCA. Bill, exactly yesterday we were trying to do that. So, as Anil said, in clustering problem where we don't have the label for the data, can we still do dimensional reduction, right?
See, dimensionality, so it's a very good question. Can I rephrase it in simpler terms?
Sure.
Irrespective of whether data is meant for classification, regression, or clustering, does it make sense to do dimensionality reduction? Does that summarize what you're asking?
So that is the question, because there is one point where we have overlap of something, and then we have to pick up through PCA like what are the most important features, and based on those features we can further take it to into consideration to develop some something like that.
So yes, so let me answer that question for you. The simple answer for dimensionality reduction is, as a data scientist, it's your responsibility to always try dimensionality reduction with complex situations. If the problem is very simple, it's all right, you may not. But in all situations, you should try to reduce the dimensionality of the problem, because A, it leads to better understanding. B, it makes the problem computationally tractable, means manageable.
Yes.
So what you should always do, invariant of what problem you're trying to solve, you must always try out dimensionality reduction. Now comes this question of what technique of dimensionality reduction will actually work. If you're lucky and the problem is linear, then direct PCA will work. Direct PCA has been there since the 1950s. Right? In fact, it was independently discovered by a lot of people, including Kosambi from my university.
Oh, DHU, yeah.
So it has been there for now, 70 years. Then over the years, the data has non-linearities. You can then try other more powerful techniques. Today, I taught you one of them, Kernel Pca. Now, when you try Kernel Pca, there are two ways of doing it. Either you let for example, the scikit library do it, and you tell it, the three kernels are linear, polynomial, and the RBF, this Gaussian. So you can try all three and see how does your data look. See, suppose one of the tricks you do is you deliberately force it to look at 2 dimensions, like x1 and x2, project down to 2 dimensions. Then 2 dimensions you can visualize, 3 dimensions also visualize. You can see how well the separations are. You draw the scree plot, you see where is the elbow in the scree plot, how many dimensions do I really need? And then there are mathematical measures to see, are they enough? There are words like proportion of variance explained. We did that in ML100, so I won't repeat that. So it just says that how good is your model, is your lower dimensional model in capturing the nuances of the full data, right? It gives you that. So you can try, if a linear model works fine, if a kernel PCA works, kernel PCA quite often works. The trouble with kernel PCA is that the 3 kernels that are built in may not be sufficient, right? You may have to plug in your own kernel. And when you try to plug in your own kernel, now we are getting into custom business. You need your own intuition into the data. That is where it is essentially a part of feature engineering. You're thinking about data, you're getting an intuition of what sort of kernel I should apply, and you can get away with it. A lot of people don't. But there are more techniques of dimensionality reduction. For example, here in my bookshelf, I'll give you a whole book, this book. It's a very good book. I don't know if you can see this book.
So Asif, can we use like TSNE and UMAP?
Yes, please hold on to that. Guys, do you see this book?
Partially.
It's a transparent book, sir.
No, we can't.
No.
Right. Okay. It is a book that I'm holding on and look into my face, not the screen.
Yes.
Yeah.
Modern multivariate.
Right. So this book actually is one of the many books, and one thing that I like in this book is it has a pretty good section. Let me go here on nonlinear dimensionality reduction and manifold learning.
So
And-
what is the book name, Asif?
Can you post that in the Slack, please?
Oh yes,
Maybe
I'll
What
do
the
it.
name?
Yeah.
picture of it and post it in the Slack.
I will do that. It's multivariate, a modern multivariate statistical techniques. In this, there is actually a chapter called nonlinear dimensionality reduction and manifold learning. That this book is very dense in the sense that you have to know our math of data science before you can even begin to understand, study it. When you do that, you will see that it has a lot of techniques for dimensionality reduction. So if you can see that, and most of these techniques have to do with something called manifold learning. You try to learn the underlying surface to which data hugs. If you can discover that surface, you can linearize it. There are all of these techniques. So like Anil was using the word TSNE and UMAP. Those are all techniques to do exactly that, to figure out deep inside what is that surface to which data hugs, and then to find a way to linearize it, bring it down, and separate it in the spaces that you look at, for example, two-dimensional or three-dimensional spaces. So the field of dimensionality reduction is very rich, especially this whole thing about manifold learning and so forth, and LLEs, locally linear embedding. I won't use those words now. We will do those perhaps sometime in the deep learning workshops. Yeah, it will be there. TSNE and all this will come. There's a whole vast literature on dimensionality reduction. So what we did today is we went beyond just PCA and I used the kernel to go to our first step in handling nonlinear data. So do that, guys. Why should you do dimensionality reduction? Because it simplifies the problem. Not only that, you gain understanding of the data. So to answer somebody's question, should we do that? I suppose your question. Dimensionality reduction is something you should always try.
Sure.
Right? You have to know. See, the question is, will you succeed? In the abstract, from a pure mathematical perspective, there does exist a space, right?
Really? Yeah, okay.
Yeah, where the data is linear. And now the question is, in that space, can you come from that space to a lower dimensional space? Like in that, is the data sort of, can I shrink wrap in that space in an ellipsoid? And when I do that, can I throw away most of the axes of the ellipsoid so that the remaining axes that I'm left with, the sum total of those axes is less than the original space from which I started. If it is true, sometimes it may be true, sometimes it's not true. If it is true, well, you can achieve dimensionality reduction. If not, you cannot, right? So for example, if you imagine data in a unit disk like this one, let's look at this data. Do you realize that this data, there is no way
I can't hear.
that you can do?
Can't hear you.
Sir,
Yeah, I think we
Actually-
lost you, Asif, for
All
some
right.
time.
I can hear you guys. So
I hear
I'll
you now.
and tell me when you can hear me.
I can hear you now.
Yeah, we
but,
can hear you
Now we
now.
can hear now.
but sometime like 5-10 seconds we lost you.
So you know, Asif, when you
Yeah.
moved to this circle and started at that point, we lost you.
Okay. So I'm saying that when you look at this data, for example, you realize that we created an axis, x3 is equal to x1 square plus x2 square.
yes, sir.
And so as far as classification is concerned, just one dimension x3 is enough, because at a certain value of x3, we could draw a hyperplane and classify. right? So from the classification perspective, we actually reduce the problem to just one dimension. Do you see that, guys? The X3 dimension. That is sufficient to solve the problem.
Yeah.
And so that's
It's a plane, sir.
yes, that's it. And that is just the height from the ground plane, from the ground of the point. Any point, just ask how high is it from the ground, and that will tell you whether it's a blue point or a yellow point. This is a classic example of how you went to a higher dimension, right? Only to come down and discover a much lower dimension that will solve your problem, right? Just one dimension became your classifier. For the classification purposes, you have reduced the problem to one dimension. That's the beauty of it.
Sir.
Yeah, go ahead.
So, sir, small question, maybe silly question. So, feature engineering, do we do before PCA and after PCA? Does it make sense? Both?
See, these things, I wish I could answer it one way. It goes around in circles. See, machine learning is not a linear process. People think of it as a pipeline. They say in production, it's a pipeline, but the discovery process is not linear. It is, you cleanse the data, you scale the data, you fill in missing values, you do outlier treatments, anomalies, and so forth. And then finally, you start doing, let us say, some feature engineering, some dimensionality reduction, then you do modeling. It looks as though it is like that, but actually it's not. What happens really is, once you have done the first few data preparation parts, the data wrangling parts, namely, you bring the data. First of all, data doesn't exist as vector spaces, right? The X, we always represent the X vector space, a column vector, right? N-dimensional vector. It doesn't. You look at the data, it exists as what? It exists as text, right? It exists as an image, it exists as a sound, it exists as columns in a database, a table, and the data is scattered across many, many tables. So one of the first things in your journey is to do those data transformations, or what people used to call ETL jobs, or things, to just bring in the pieces together and build the X vector. Once you have built the X vector, then you do all of these. You do the cleaning of it, the anomaly detection, the missing value treatment, and all of that. And then you prepare that into it, you create the cleaned out X vector. But you still don't know if these are the right feature vectors to go into your algorithm. You don't know, right? So what do? Then many things can happen. Maybe there's a lower dimensional space that represents it. Maybe there is another vector that we can build out of it, the feature engineering like we did for river. Or like you see in this problem, it is not X1 or X2 that matters, it's X3 that matters.
Yeah.
So how do you discover X3? Then you start going around in circles. You partly use intuition, partly try SVM, partly try different techniques. And you see that when they begin to work, you ask, why did it work? Can I, for example, use it, go back and do something? So in reality, after X, there is a journey to, let us say, X prime, the feature engineered vector, the feature vector. And this is the thing. Usually the input vector and feature vectors are different, right? So this journey is sort of an iterative process. You go back and forth. You go all the way to the classification and model building, and you keep coming back. And it is the circle of learning, somebody used to, I suppose in US, we teach children a very simple phrase that science is captured, the scientific spirit is captured in 3 words that form a cycle. You ask a question, is this true? You start with a hypothesis. Then you measure, you gather data to test the hypothesis, get the data in. Learn from that. What did you learn? Did it support your hypothesis or not?
Sir.
And then you come up with a different hypothesis. You go back to asking the next question, right? So you are forever in the circle of ask, measure, learn. And that's how you build better and better and better models. And this is the classic journey of science, right? So you keep going in circles there. So any non-trivial science project you do, that is the reason it takes a long time. See, I'll give you a real life intuition.
Sir.
In your career, for most data scientists to be successful in their workplace, they don't work with too many data sets, here we are doing different data sets at a time. We're getting practice. It's good for learning. In workplace, you will just get one kind of data set. Maybe you're working for, I'll take a hypothetical example, Zillow. All the data set will be about real estate, isn't it? And one team will be trying one sort of algorithms or variations of it for a long, long time before they have a breakthrough idea and start trying different algorithms. Right? Quite often they'll be like, going around in circles, trying to optimize, make it better. The predictions for just one problem. In the case of Zillow, it's like better predicting the house value, let us say, right? And then all sorts of other sub problems associated with it. You can keep building models. So your entire career there in a team can be associated with solving one problem. So obviously it can't be a linear problem that you went through the journey correctly and you have a model. No, you keep on moving around in circles, getting better and better and better models, which also sometimes means finding the right features or right inputs and then asking people to go gather those inputs. Right. And so that is how data science works. Are we together, guys? So all right, today I covered the second topic, which is kernel PCA. I would like to, before I go into the break, cover one more topic, which is using the distance kernel for KNN. Okay. So should I'm closing this topic, guys. Should I, do you want to take a break before we start on the next topic, or can I start on the next topic and then take a break?
As if I had a question.
Go ahead.
Sorry. As if we use a kernel to express our data on a higher dimension,
Yes.
does this simply translate the understanding of the data into something that's easier to wrangle, or will this transformation introduce a likelihood for variance errors?
No, not really, actually. When you go in a disciplined way up to higher dimensions, you don't necessarily, to my knowledge, introduce a lot of variance into the problem. Look at this thing. From here, the circle, when you lift it up to the parabolic surface, it was a very controlled function, isn't it? It was just not a haphazard expansion of the dimensionality of the problem. You don't, you're not introducing more variables, more flexible parameters. It's a very disciplined approach to go there. So this won't affect your directly your bias variance trade-off, at least not in an obvious way.
Okay, thank you.
Yeah. All right, guys. So we did something. I can see that we did something conceptually a little bit heavy. At this point, would you guys prefer taking a short break to absorb all this? Think about it, and then we'll start in 10, 15 minutes.
Yes.
Yes.
Break.
Yes, that works.
Let's do that. Then we'll come back to. So today, guys, we'll have 2 breaks, perhaps, or maybe one break and a very long session after this, because we do have a long session after this. I'll pause the recording. See you guys in 15, 20 minutes.
Thank you.
All right, guys, let's start getting back.
Hello.
Yeah, we have pretty good participation today. Nice. So, guys, this is a question that came up, I think, is that how many contact hours are there in the boot camp, and how does it differ from the workshop? So, here's the difference. In the workshop, officially, there were every week 5 contact hours, 2 days a week, 2.5 hours, 7 to 9:30. That was the official or the promised, the guaranteed one. In reality, we are doing, we are obviously doing the 2 evenings, let's say 5 hours, sometimes it goes more. And then we are doing the Saturday and the Sunday sessions. So I would say that we are probably doing about 7, 8. Would it be fair to say about 8 contact hours a week in workshop?
Yes.
Yeah, 8 or 9. 8. So promised was 5. We are doing about 8. In the boot camp, the promised number of contact hours is we are going to do 2 weekdays, evenings, what we are doing in the workshop, and all of Saturday, right? 12 hours on Saturday. I will be there. In other words, I will be helping you guys from 10 a.m. till midnight. But if you finish your projects earlier, you can leave. So that will be the, actually more than 12, it's more like 14 hours, but still let's call it 12 hours, 10 p.m. Close. And we will be doing the 5 hours during the regular week. And then those extra sessions will still continue. The reason I made it 2 weeks, 2 days, is because I expect that the extra sessions will be the other 2 days. So in practical terms, when you're doing the boot camp, you will be spending a whole lot of time with me. You'll be spending more like every evening, other than Friday evening, you will be spending with me. And the Sunday, I'll again be giving extra time. So it will be more like 20, 2.5, 2.5, 10 hours during the week and 12 hours during the weekend. That's 22 hours and 3 hours on Sunday. So 25 hours a week. So all of it put together will come to 25 hours a week. So it will be compared to 8 hours that we are giving here, it will be 3 times more intense. Right? So be mentally prepared for that. That when we do the boot camp, we will take it very seriously. We'll do a lot of work here. We develop the theory. There, what we will do is on the weekdays, we'll develop the theory. The way it will work is on Tuesday, or maybe actually I'll move it to Monday and Wednesday. On Monday, we'll do the theory just as we do now. On Wednesday, we'll do the lab, walkthrough lab, guided lab. Then in between, Tuesday, we will do our quiz session. On Thursday, I'll do the extra help session, coding help sessions, and so forth. And so that all of it is preparing you for the actual project session, which will take all of Saturday. Right? So it will be 25 hours of engagement that you'll get from me. It all amounts, and you will have to put in those minimum hours. Of course, you'll have to do more work in the background study and so on and so forth in the material. So all of it put together, it's 100 hours. So it is 100 hours. For those of you who are taking only workshop, 100 hours at $1,000. So that comes to $10 an hour. I suppose that's a fairly below market tuition rate in Silicon Valley. But so that's that. But if you're taking,
even it is below like a federal rate, minimum rate.
Yes, below the minimum rate. Yes. So that's that. And if you, of course, are going to take all 3 of the boot camps, the deep learning, the whole sequence, then it is even less than you are paying $800, which comes to about $8 an hour. Of engagement. So that is the way the economics of it works out. Now, so that's the economics of it. But then, guys, when you come to the boot camp, You have to be mentally prepared. It won't be like the workshop. It is the workshop plus much more. It'll be intense. You'll have a lot of fun. The projects will be there every Saturday, twice a day. Your team will be making presentations. So use this time in ML 200, and deliberately there's a 1.5 months gap to brush up on your programming. The people who got the most out of the workshop, the boot camp, and all of them got a lot out of it, most of them, I would imagine, they all did become very comfortable with coding, and they had fun, solving the problems and presenting their own team solutions and so forth. So the pleasure of a boot camp is that it is not just one-way traffic. It isn't that I'm teaching you. That will happen during the weekdays. The sheer pleasure of the boot camp is what you bring forward, under guidance, of course, what you guys bring forward as a team, and what you bring out as presentations. It builds up your confidence, it builds up your resume, and it helps you create good notebooks and blogs and things like that. Right? It essentially establishes your confidence. So you will do half the work, or more than half the work. Right? You'll do the projects, and I'll be guiding you on Saturday. In this workshop, I'm expecting you to do the project. I am there to help you, but it's not a mandatory part. I mean, I know that some of you haven't yet gotten started with the project. That is not good. You should start. But in the boot camp, project is a central part of what we do. You'll do fairly long projects. You'll learn a lot. You learn amazing things from images. Imagine looking at X-ray images and being able to tell COVID, being practical things, being able to tell a tree from another tree or something like that, classification, being able to do a lot of this, textual analysis, summarization, many things, being able to detect whether a face belongs to a person or not. Right? So for example, if I have just one picture of you, can I make sure that the person that the camera is seeing walking towards the door is you? Those are very practical situations. So those will all be in the projects, and we'll do that. Obviously, at the end of the workshop, I'll give you the solutions to the project, but usually you don't need to, because all the teams succeed in creating some solutions, and they all showcase it, like they present it at the end of the day to each other. So I hope I answered this question that was coming. How is it different from the boot camp?
Asif, I have two questions actually. One is on the Saturday session, you say, will that be in person?
Oh, unfortunately, Sanjay, we know we live in the COVID world is exploding. It won't be in person, but one of the things that has happened is in the last few months, we have all in the educational field been developing means to make it as real as possible. So it will be very real for you. What you'll miss is the lovely food.
Yeah, I do.
Food.
The other question I had is, would you have some break, after the between first and the second month and the second and the third month, or would you go like 3 months, boom, boom, boom?
No, actually what happens is at the end of each month, we will give a small break of 2 weeks, is because a lot of people, for example, the experience was that they like to clean up their notebooks, because during the boot camp, you're rushing forward. Then people like to publish it, or put it on GitHub and so forth, showcase it, public GitHub. So in showcasing, they ask for time to dress it up, essentially. Right. So we will have a small gap between the sessions, but very small gap. I don't want the continuity to break. So it will feel like contiguous. We'll just miss a week in between, that's all.
Yeah, Asif.
Yes, go ahead.
So this this you are talking about the deep learning bootcamp, right?
That is true.
So is there going to be like, are you going to have the deep learning bootcamp after the math, or it will go in parallel, or how long the math one takes basically?
The math is going to be a whole month of intense, like it will be a little bit more intense than our current workshop. See, our workshop was 6 weeks, right? So we'll squeeze the same number of hours into a month, right? We will have, so that you can have a little bit of a gap between math and the next one, the boot camp. but it will be one after the other.
Oh, it will be, so you will do math and then your deep learning will start.
Actually, the math will be 5 weeks, but we'll squeeze a little bit more material than the ML200. See, as you notice, right, in ML200, are you guys getting the feeling that we are covering more than ML100? Anybody? Or that was the intention, that we cover more territory. Anybody feels that we are covering more than ML100?
Yes.
Yeah.
Certainly covering more material. So I'll dial up the pace. Every successive workshop that you take, the pace will increase, the material, the amount, not just it will be different material, but the quantity of material will be more. So the the math course will do the entire 400-page book. But if you remember, in the ML100 and ML200, we are taking essentially 2 courses to do the 400-page ISLR book. In the math one, we'll cover the whole book. Well, not exactly the whole book, but a large part of it in like 5 weeks, essentially, 4 to 5 weeks.
Okay. And then deep learning bootcamp will start.
Then deep learning. So in other words, gear up for momentum, guys. These may be the most intense years or months you have gone through after your college. But that is the whole point. You want to learn it deeply and thoroughly. Right? So get up for that and you'll have a lot of fun. People had a lot of fun in the last boot camp.
So Asif, approximately when deep learning is starting? Is it
Oh,
September?
it's announced. It's 1st September. There is even a sign-up link. Prachi, could you please put up the sign-up link again on the Slack?
Yeah, I'll do that.
Do that. I don't know how many of you have registered, but I would encourage you. I mean, personally, right? When I was learning all of these things, obviously, I come from a different culture. I mean, we used to read, we used to spend, I took a lot of time, and I'm talking about 25, 30 years ago, right? Picking up these things, but it was still not a very big field. But whatever it was mostly through self-study and asking and the professors and begging them for time and so on and so forth. That used to be the world. Now, I am essentially this trying to be, I don't know how successful I am, but I'm trying to be the professor I wish I had when I was learning these things. So go at it, guys. See, the return on investment is humongous. I mean, even if you look at it not from the joy of the subject, but from a pure financial perspective. A typical software engineer these days makes what? In the range of 130 to 160 base salary. Right? A typical person who has skills that we are learning, their base salary starts north of 200K. What does it take? A little bit of money, but more than that, a lot of just 6 months of your life. You give up 6 months of your life to working very, very hard, genuinely working and picking up the material, not slacking. And then you come out at the other end, and would you rather not earn 50% more than you're earning today? So even financially, it makes sense. So, so the boot camp, I would say that. I mean, and I'm not saying
that's the carrot.
Come again?
I'm saying that's the carrot.
That's the carrot. Yes, that's sort of the carrot. Yeah. So, guys, I'm not doing it because trust me that my day job compensation is pretty good. I'm not doing it to earn money, though the money is a consideration. Support vectors is tanking at this moment. It's a negative. And so I do want to break even and all of that. There is a bit of financial incentive, but that's not the real reason I'm asking you guys to register for the bootcamp and so forth. It will genuinely help you. So if you, and this math and all of this, if you have started on this journey, finish it properly. It will benefit you a lot. It will, and you can, those of you who are in college, you can give it a contrast with what you learn in college. Ritvik, it's nice to see you here, Santa Barbara. Ritvik, can you hear me? You're on mute. All right, Ritvik is on. Yeah, and no. All right, so we could have asked him how. So he'll tell you, like, how does this courses compare to the ones in college? It's a different experience. It's much more intense. All right, guys. So with that, I'll get back to the subject. So yes, we'll have math, and we'll have math. Actually, I have to announce. Prachi, do remind me to start the announcements and the registration for math immediately. I have been too busy with all of this.
Asif, how long is what's the duration of the bootcamp class in September?
4 weeks or 6 weeks?
No. The boot camp is 4 weeks.
4 weeks.
But it is 100 hours. So let me put it in perspective.
Yeah,
This
I got
right,
that.
used to be 30 hours, 5 hours a week, 6 weeks. That is 100 hours. So you'll be, as Sandeep went through the boot camp, ask him.
Yeah.
How intense it was, right? So,
Yeah. But that was just on Saturdays, only on Saturdays, right? You try to pack everything in on Saturdays.
No, Kale, let me re-emphasize. You will have Monday, Wednesday, and Saturday formally. Tuesday will be quiz, and Thursday would be the coding help sessions and so forth that I gave. See, at this moment, what do I have? I have 2 official sessions and 2 unofficial sessions. Official sessions, that is the promised ones, are the Monday, Wednesday. Monday theory, Wednesday lab. Then we have Saturday for quizzes and interview questions. And Sunday we do, or Saturday sometime we do another coding help and Python or R or something like that. Right? So these 4 sessions will continue, but the dynamics will change. Monday, Wednesday will remain theory and lab. The quiz will move to Tuesday. The extra help sessions will move to Thursday. So the Thursday will become optional, but at least the first 3 days, Monday, Tuesday, and Wednesday, will strongly suggest you attend. Then all of Saturday. So the only day really you are free.
No, I got that. I was talking about when Sandeep did the boot camp, it was just only Saturday, right?
Okay.
It is not the same. This is much more intense. It was spread over 12 weeks and it was only Saturdays.
That is right. And this is also spread into a 12-week scale. It is 3 boot camps, but each boot camp is way more intense than the October boot camp. Right? In other words, you'll have a lot more to learn, a lot more engagement and so forth. So,
Asif, did you consider 6 weeks instead of 4? Just checking, because this COVID days,
no, see,
people are working 150% now.
Yeah, so we will calibrate it. Huh? Let us start. If you guys feel it's very intense, see, it's our workshop, it's our boot camp, guys. If all of you feel we need to slow down a little bit, we'll slow down a little bit. Right? But let's not give up already. Let's start and see if the intensity is too much, we'll slow down. How about that?
Sure. It's more about finding those many hours to spend on that. That's where the concern is coming from.
Yeah, I'll give you a tip. When you're in grad school and doing research in one of the top places in US, there is a basic rule. If you get a good night's sleep, you should pretty much feel ashamed of yourself. Anybody who has been through that experience in grad school? Shankar, you must have gone through that.
Sorry, I missed the question, Asif. What is it? Something about grad school.
Grad school, right? When
I got through that experience in an undergraduate math class.
Oh, you did? Yes. So
definitely.
Yeah, you learn most when your mind has no space to think anything else. Like you're 100% occupied with one subject, one topic. That's why in grad schools here in US, the good ones, you are working on something all the time, and you practically feel guilty if you get a good 9 hour sleep. Most of the time, you are working very hard during the weekdays, like getting 5-6 hours of sleep and getting back to work, and you're sacrificing weekends to study and so forth.
Oh, the first weekend I took was on my birthday after 1 year. After coming to US and working all 6-7 days in grad school, the first time I took a break on my birthday the following year, and I felt guilty about it.
Yes. That's how it is. So guys, obviously I won't push you that hard. I know that you all have families. Working is hard with kids at home, and work expectation paradoxically has gone up. Employers have found out that it's an unfortunate fact that employers have figured out that you can push people to work harder when they work from home. They're getting a lot more productivity out of people. And people are struggling because they have kids at home. They have many other everything. The maid is not coming for those of you who do use a maid, and so forth. So everything falls on you. Let us put it this way. Let us aim high, and if we need to slow down, we'll slow down. How about that, guys? Does that seem a good framework?
That sounds fair.
Yeah, let's start there. And we'll take it. We will know how much we can push through. It is, I would, so to your question, I would easily expand it to, if needed, 6 weeks, if needed, 8 weeks per workshop or per boot camp, doesn't matter. The point is I have a certain quantity of material that we have to cover, that we absolutely have to cover, the syllabus, right? So whatever time it takes to cover the syllabus properly, we will take that time. And hours don't matter, right? We'll just keep at it. Does that become
this
more?
time,
Yeah.
Asif, Prashant here. This time, can you just publish what are the you are covering for each of the bootcamp 3? That will be easier to get settled down on that.
Yeah. So yes, see.
I actually did some updates in the Slack.
Right, yes, I could drop some updates. So basically, guys, Bootcamp 1 is foundational. It will give you understanding. It will get you started in every area or most areas of deep learning. It will get you started with natural language processing, text processing, the transformers, the RNNs, and so on and so forth. It will get you started with image processing, the CNNs, convolutional neural nets, and so forth. It will get you started with how to deal with embeddings, word embeddings, graph embeddings. Yeah, you'll get started with graph neural networks and graph embeddings, and the embedding of any categorical variable, and tabular data. How do you deal with tabular data? And it will get you started, most importantly, with something that for some reason nobody seems to be teaching, but it's very, very important. It's automated machine learning. How do you create, okay, so let me give you a bit of a background. See, it is actually part of your next lecture, but let me give you a hint about that. Do you notice that with support vector machines, with trees, and already you're getting algorithms which have a lot of hyperparameters. Do we understand what hyperparameters are, guys? Like, for example, in a forest, how many trees to have? How deep should each tree be? How many features should each, at each split point a tree should look at? These are all hyperparameters of the model in support vector machines. Which kernel to take? Or what should be the parameter of the kernel? Like, what should be the gamma for a radial basis function? What should be the degree of the polynomial, and so on and so forth. So in every complex algorithms, there are all these hyperparameters. And the difference between tuning the hyperparameter and not tuning the hyperparameter is vast. So it leads to all sorts of theories on how to find the best hyperparameter. If you look at the books, they tell you that, oh, the way to do hyperparameters, find the best hyperparameters, is to do something called grid search. Maybe that's sort of the kindergarten of the field. Then you can do randomized search and so forth. But actually the state of the art has moved ahead. Today, we have an ability to do very efficient search through the hyperparameter space and find the best classifiers or the best regressors or whatever it is you want. Let's take classifiers as an example. The best classifiers. You can tune them and the performance gains are like huge, very, very impressive performance gains of the model. And not only that, I've taught you so many algorithms now. You have learned about decision trees, random forests, support vector machines, logistic regression, a linear discriminant analysis, quadratic discriminant analysis, and this and that, and many things, right? So the question is, and each of them will come with some hyperparameter tuning. So how do you search for the best model for your data? And therein comes this field of automated ML. There's a whole body of research and this breakthrough work happening. For strange reasons, at this moment, it hasn't made its way into textbooks yet. It will. Maybe soon you'll hear that this is the latest. So we will cover automated ML in a big way. So again, deep learning foundations, textual, the audio visual, and graph, and automated ML. These are the 6 topics of the first workshop. The second workshop will take it far deeper. Second workshop will focus on convolutional neural networks. And we will do all the powerful techniques that are important today, like we'll bring in the residuals and the tuning. A lot of things we'll do focused on convolutionals. The third workshop is completely focused on transformers. Actually, I might do transformers before I do so second and third are interchangeable. I'm actually inclined to do natural language processing before, the transformer before. Those of you who came to my attention is all you need to talk. You pretty much have an idea of what we'll be going through. We'll do all of that, attention, transformers, RNNs, all sorts of text processing, embeddings, and so forth. That will be the third workshop. We'll go pretty deep and do pretty large projects, or rather bootcamp.
So
And
these 3 workshops, ML400 is all of those, 2 of those?
no. ML400 is the first. 410, 420. There's 400, 410, 420. Right. So the one that I just released is only the ML400, which will cover those 5 topics. Actually, there's one more topic, which is anomaly detection. Time permitting, we'll do that. So every day, like the first day will be a bit lighter. First week, I'll get you through the whole foundation. But every 3 successive weeks, we'll cover about 2 topics a week. Right? We'll move fast. Whereas in the subsequent workshops, we'll move deep.
Asif, in the subsequent workshops, the second and the third one, what are the domain verticals, if you can tell us, that will be covering in terms of like NLP or
Yes.
others?
Yes. So this one workshop after that will be purely NLP, completely NLP.
Okay.
Are we together?
Yeah.
Not see, it will use transformers and so forth. They can be used for even for images. So let's say that 90% of it, but people are finding non-standard uses for all of those theoretical constructs. So we'll do all that. Then another workshop will be, another bootcamp will be entirely devoted to going really deep in the computer vision part. Right? Okay. See, here's the thing: when we do deep learning, right, I won't be covering much of computer vision theory.
Okay.
But if you really want to do image processing, it isn't just a neural network. You have to know the subject.
Okay.
So we'll also do the theory of computer vision, the formulation of computer vision. So we'll go deep in that workshop. See, the idea is, guys, that my goal is, and I hope I reach it, is that by the end of all of this, when you are done, you guys come out in the top, hopefully at least the 10% of the data scientists are anywhere with any level of experience, and at least 10% and hopefully better, more like the top 3-4% of that, or 5% of that. Right? You go through a rigorous training, it's really worth it. Andrew Ng, the guy who founded Coursera, he used to make a very interesting joke at Stanford. I haven't seen him make that joke now, but when he was younger, when you would take his Stanford course in machine learning in those days, that course is still there. I believe, what is it called, 223 or 225 or something like that. When you would take that machine learning class, you would submit your first homework on linear regression. By now, guys, you must have realized that linear regression is the kindergarten of this field, right? Everybody starts with linear regression. It's very powerful. It gets a lot of things done, but it's straightforward. Like the theory is relatively straightforward compared to all the things that you learn after that. So you would submit your homework, and then Andrew Ng used to congratulate students in the class. He says, "Congratulations, you are all now bona fide computer science, like AI specialist or machine learning specialist." And they would say, "What? Are you kidding? This must be a joke." And then he would say that actually it is a joke, but there's truth to it, because most people who walk around Silicon Valley claim to be machine learning experts happen to know less than what you know, which is the tragedy. Is still true, I believe, in this field. Most people are, they have picked up scikit-learn, they have picked up the libraries, TensorFlow, Keras, etc. They are all people who are mechanics, who are just using the tools to get the work done. And they are not people who understand machine learning at all, deeply. What I'm trying to do is build you guys up to be permanently in this field with a deep understanding. Right? So that's
the basics.
The foundations, yes. See, what's the difference between a doctor and a nurse? Right? There are many ways the trade-offs are there. Nursing tradition starts with Florence Nightingale. It's focused on caring. Yeah. But they go through. But if you look at emotionally, the nurses take care of you a lot more than doctors do. Doctor will come, look at you, give a prescription, walk off, right? Give a consultation and walk off. But I say that as a child of a doctor. But if you look at the intellectual, nurses are trained in medical sciences, doctors are trained in medical sciences. The difference is the depth and rigor, right? Doctors go through far deeper, more rigorous training in the subject, isn't it? By the time you become a specialist in cardiology, let's say, or anything, neurology, you have gone through years and years of rigorous training, and steady. So that's the difference. And the point is that if you are in a field, be a master of the field. Don't be one of the, one more guy on the street.
Yeah.
So anyway, that's a long interlude, guys. So I'll get back to the subject at hand. Any other questions before I start the recording and we get back to the subject at hand?
As if regarding the coding in the bootcamp,
yes.
Will you also talk about like quantized aware training, like for edge computing, or is that another topic on its own?
Oh, no, not in the first bootcamp. Oh goodness! But you do remind me of something that I should cover. In fact, Medal keeps asking about this. See, guys, you won't till now. You have just been building the model and testing it out, right? And you're feeling good. Okay, I built a good model. But at the end of the day, in real world, you take your model to production. You haven't, because we had limited hours, just 5 official hours a week in the workshop. You have not taken your models to production, isn't it? So, okay, actually, that's a very important part of the bootcamp. In every bootcamp, all the models that you build, we will take it to production in the cloud. Your team will have to deploy it to the cloud. And I'll take you through the whole process of deploying to the cloud. You will have to have a full end-to-end application, a front end to it. Right? Simple front end, it need not look pretty, but you will have a real experience, end-to-end experience of what is it to build a practical machine learning or an AI application, end-to-end. So the journey will not stop by saying, oh, look, I'm getting good predictions. But that is all right for ML 100, 200, but those days will be over now. Now we'll make it very, very real. So at the end of it, your transition from the bootcamp to the job should feel like a no-brainer. Right? You will be doing a lot of real life what you do in the workplace, but you'll do it at a much faster pace. In the workplace, you do it in 6, 9, 1 year time frame. Here, you'll do it in a month time frame. It'll take, in fact, weekly time frame. Every single model that you build, you will take it to production all the way. You'll create an inference engine. And for example, you should be able to, from your cell phone, use it. Are we together, guys?
Yes, that will be awesome.
Yeah, that is actually a core part of doing it. Bootcamps gives you more time, like I said, right? 100 hours of engagement gets you a lot of time to learn a lot of things. So we'll learn a lot there. All right, guys. With that, any more questions? Otherwise, I'll get back to the main thing. We should get back to our stuff now. Should I start the recording now, guys?
Sure.
Okay. So guys, to recap, what did we do in the first part of the session? The first part of the session was that we were trying to get an intuition. Why is it that when we go to a different space from the original input space, quite often, and usually a higher dimensional space or just a transformed space, you can see that the problem has become much simpler. It has become a linear problem, and therefore you can build linear decision boundaries. For classification and for regression, of course, you can do a linear regression in effect. And for dimensionality reduction, your old technique of Pca, for example, can be applied. You just need to take a kernel. You need to go to a higher dimension where the problem is straightened out, so you can wrap an ellipsoidal shrink wrap around your data and then go about doing your Pca thereafter. Does it always work? Not necessarily, but it does work a surprising number of times. You should certainly try it. One of the questions that was raised is, if I do kernel Pca, will I always succeed? The answer is different. First is that the built-in kernels in the libraries are limited, linear, polynomial, and the RBF. If you're capable of growing your own kernels and thinking through the data, this is again feature engineering. You might have much more success, but if you use the vanilla one, you may not succeed. Yeah. You may not have as much success. The second aspect that comes to it is that the problem truly cannot be reduced in dimensions. It takes the whole space. For example, you would agree that this problem is something that looks as though it's actually, this is a simple problem. We could reduce it to one dimension, the z-axis, the x3 axis, but there are problems which cannot be reduced to lower dimensions. Truly, information is scattered in the entire volumetric space of the feature vector space, right? In the entire volume of the feature vector space. Then you can't do dimensionality reduction. And lastly, not every technique has its limitations. So kernel Pca, while it is more powerful than Pca perhaps, well, powerful is itself a word, not always more powerful, sometimes more powerful, but it's not so powerful that it can handle every situation. So the field of dimensionality reduction is rich. There are many, many algorithms, just like for classification and regression, there are many, many algorithms that you use to be able to classify data. So there are many techniques for dimensionality reduction. It's a very rich literature. There's this whole field of manifold learning and so on and so forth. We'll learn it, and they're beautiful visualizations, the TSNE, the UMAP, and so on and so forth, which you'll get very hands-on experience in the next class, the bootcamp. But here we won't have the time for that, but I'll stop here. What we will come to now is we will see how we modified Pca to get dimensionality reduction. We can actually modify K and N to make it a little bit smarter. We'll use distance kernels. So the idea is this. See, I told you that if you have a point here, where was I? Let's go back to our motivating example, the cows and ducks. So suppose you have your ducks here. And now you guys are familiar with this example, so I wouldn't draw too many points. And let us say that you have cows here in the feature space. And obviously the way we motivated this is by saying this is weight, x1 is weight, and x2, let us say, is the size of the animal, right? Very intuitively obvious that ducks are small and lightweight relative to cows, and cows are rather big and heavy creatures way out there in the feature space. Obviously, spread will be more, so I'll spread it out a little bit more. Okay, something like this. So the question is, this renders itself very easily to birds of a feather notion. If you want to find out what is this point, this guy, it is, you look at the neighbors, or this guy, you look at the neighbors, it's pretty obvious that things this size and this weight are much more likely to be ducks rather than cows. You look at this point, you don't have data for this point, you get an animal whose weight is that and size is given by that value. And intuition says that it must be a cow because things similar to it are cows in the feature space, the neighboring points in the feature space. That is the intuition between K and N, K nearest neighbor, nearest neighbor. But then I also pointed out that this has a limitation for it. So the limitation comes from the fact that suppose I bring in some things that are bigger in size, but not as heavy. I don't know. I cooked up giraffe, but biologists will please excuse me if this analogy is wrong in terms of weight and so forth. So let us say that this is it. So how do you know whether something is a cow, a duck, or a giraffe? You can say, well, I'm going to look at the neighboring points, but then the one problem that remains is how many neighboring points? If you take K is less than 1, I'm just recapitulating what we did. If you take K less than 1, oh, sorry, not, what am I saying? Silly. If you take K is equal to 1, you can often get it wrong, isn't it? Accidentally or by chance, more likely, that the nearest neighbors may be of the other kind, isn't it? So let's look at this example. Suppose you are here. Which point should I take at this point? Do you see this point that I drew with the small, where my mouse is, guys? Yeah. This point, if you ask, what is it? Is it a giraffe or is it a cow? You'll be, if you use K is equal to 1, the answer would be, it's a cow. But if you take K is equal to, let us say 3, now you'll say giraffe, isn't it? And let us say that you have, in this particular meadow, you have a lot more ducks around. Let's say that in your data set, there are hundreds of ducks. So now, suppose you take k is equal to 200, let's say. What do you think your answer will be? It will be the entire data set. And what is the majority here?
Duck.
Duck. So you will end up with an answer of duck. So you notice how your answer varies as you go from here to there. This is the traditional journey from high variance to high. And so let me connect it to this concept of high variance to high bias. Right? At k is equal to 1, you are in a situation of high variance, overfitting, to a situation of k is large. Let me just say k tends to infinity, high bias. In fact, in k is equal to infinity, obviously you won't reach infinity because you have finite number of sample points, but it's in practical terms, whatever the sample size is, n, you will end up with a situation of bias, and it will degenerate into the baseline or the 0R classifier. What a terrible spelling I have. A degenerate rate into the baseline or 0R classifier. What does the baseline or 0R classifier say? Its answer to every question is the majority, right? Whichever is the most common. So in this space, cows, ducks, and giraffes, it turns out the ducks are most common. So a baseline classifier doesn't care about anything. It won't even care about the neighborhood. It will always answer the answer to any question, what animal it is, it's a duck. Right?
Is k the number of neighbors?
K the number of neighbors, yes, indeed. Thank you for asking that. If I didn't clarify that, k is the number of neighbors. Huh? So it is the hyperparameter in this model. So, I mean,
the value of k, the k equal 1, give you a high bias? Too simple?
No, high variance. You will see why. It is the decision boundary is very complex and very sensitive to. If you take another sample of data, your answer will change, and I will illustrate that point in a moment. Right? This is something you should know actually. This is it. So this other end is easy to understand, isn't it? If your answer just simply doesn't change, irrespective of what you do, you're in the state of obviously an extreme bias, and there is no variance at all in your answer, isn't it? Zero variance. So it's, I remember, if I may just say, there was almost a silly joke. Once I encountered a fairly silly book somebody had written, and the title of the book is Quantum Explanations or something like that. And I was very fascinated because I used to love theoretical physics. I picked up the book, and in the book, the explanation of every phenomena was this mythical thing called quantum foam. So everything happens because there's a quantum, right? So obviously, it was rather a silly book. I was disappointed, and I felt like a fool spending money on it. But that's that. So a high bias situation is like that. The answer to every problem is just duck. Right? What, I have an animal, this is the weight, this is the size, this is it, this, that, all the attributes, and what's the answer? Is duck, right? So it is your point, it's one extreme, it's a 0R classifier.
This doesn't depend on the data.
Absolutely doesn't depend on the data. That's why it's called 0R. It doesn't look at any of the features at all. One answer for the entire feature space, right? So now, what is the journey from k is equal to 1 to k is equal to n? And how do we illustrate this? So I'll illustrate this with an example. And in the notes, I give more examples. But here, let me take some simple motivating example. I'll make a different picture here. 2, 3, 4, 5, 6. Right? And now let me take some points. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let me just bring in some errors. This. And while we are at it, something like this, and then blue points also, let me throw in something here and a couple of things here. So guys, let's try to build a decision boundary. Let's take an arbitrary point. Suppose I take a point here. What will this be? This little point, what do you think it will be? Clearly, it's a yellow point, isn't it, guys? It seems, suppose, and we are taking k is equal to 1, one nearest neighbor. So what is the nearest neighbor to this point? Guys,
yellow.
It's the yellow. And then it will be yellow, yellow, and the nearest neighbor to this point is blue. You would realize that if I take the perpendicular bisector of this, the decision boundary has to be here, isn't it? Then you look at, then again here, any point that you take here, between these two, once again, you'll build a decision boundary somewhere, actually somewhere close to this triangular space. Somewhere here, the decision boundary will go. Then it will go through here, right? And then it will go through here. Do you see how we are doing the decision boundary, right? Through here. And it's getting complex, but okay, I will sort of, and then it gets even more complex. I don't know how to deal with this, but we'll deal with it at some way. It goes up here, it goes through this, and then it goes through,
comes back,
comes back, and then goes through like this, right? Something like this. You get your k is equal to 1 decision boundary. Keep the shape in mind. I'll just make it a smooth curve, even though it's actually made up of little
many perpendicular bisectors.
Exactly, it's sort of those lines, those edges. So this is your decision boundary. Now keep the same thought in your mind, and I'll use a different color. Let me use the green color, perhaps, for k is equal to, let's take k is equal to, how many points are there? 3, 7. K is equal to 3. Let's look at k is equal to 3. Go back anywhere. You realize that up to here, right, very close to it, it will actually be the 3 nearest neighbors will be, if you look at this, let's ask about this point. What are the 3 nearest neighbors? 1, 2, 3. So it will be declared as blue, isn't it? This point is blue. What about this point? It will be declared as 3 nearest neighbors are 1, 2, and which one do you want to say? This one, 3 nearest neighbors. So what will you declare this point to be? Blue, right? This will still be blue. What about this point? This point itself, any in the vicinity of this point would still be blue. Do you realize that even if you're sitting on a yellow point, if you take the 3 nearest neighbors, it would still be, depending upon neighbors you are taking, these neighbors, it is still a blue point. So what is happening is that your decision boundary is going much more smoothly, right? Now let's look at this point. What are the 3 nearest neighbors? It is yellow. So it will go something like this, right? So far. And then here, these are the blue neighbors. This is yellow. Let us look at this point. Where are we? 3 nearest neighbors are yellow, right? So it will turn around. It will, now we ask this question, what about this point is yellow? What about this point? This point is blue. If you notice, the 3 near, okay. The 3 nearest neighbors are, I don't know, depending upon how you look at it. Let me cheat a little bit to simplify the picture. You would say that this is blue. This is blue. Do you realize that? Okay, suppose, let me make the problem a little bit more to make the meaning clear. And there's so forth. Add some more points. So you realize that I mean, obviously I'm cheating a little bit here. Your decision boundary might be like this. What can you say about that versus the white decision boundary? Do you notice that the white is far more curvy, isn't it? It's more complex.
Yeah.
And now let's take k is equal to 6. Let's take another color. I'm just taking illustrative examples here. And let's take this. K is equal to 6. Then what happens? the problem begins to simplify quite a lot, actually. I would like to believe that if you are here, most of your neighbors, let's look at the 6 nearest neighbors. 1, 2, 3, 4. These 2 would be the nearest neighbor. 5 is, and whether this is the next neighbor or this is the next neighbor depends upon where you are. Let us say that this is it. So this point is still yellow. And if you draw this decision boundary, perhaps it would be even more smooth, actually. How would it look like? I don't know. It would probably look like something like, let me just simplify it, right? Pretend, I don't know if this is something, but I'm trying to just develop the intuition and perhaps cheating a little bit in my point, but we'll do it actually in code and you'll see it much more realistically. So what can you say of the decision boundaries? Do you notice that the decision boundary keeps getting less complex? Keeps getting less complex, isn't it? In the asymptotic limit of k is equal to, let's say that k is equal to the maximum number of points, whatever it is, let's say 20, what would be the answer? Majority. Which points are more? 1, 2. I clearly see blue points are more. So what will be the decision boundary? Here. It will say that all points are blue because I have more blue points. Are we together, guys? If you look at k is equal to 20 and you take 20 neighbors or 25 neighbors, your answer will always be that all points are blue. And you have a very simple decision boundary. What is the decision boundary? Everything is blue. You can just put any line beyond all the points and put all the points on one side, and that becomes your decision boundary. Actually, it is even more extreme. Your decision boundary can be anything, like something like this. Oh, sorry, that is, let me use the right color. It could be anything like this. So all the points on this side are blue. Is this obvious, guys? Are we making ourselves clear? Right? So decision boundary becomes less complex. And so now what happens? Think about it this way. If I take another sampling of points, this decision boundary will not change. But on the other extreme, k is equal to 1 will change. You would agree that if I took a different position of the blues and yellows, the decision boundary will immediately shift. Is this point obvious, guys?
Yeah.
Right? So a different sample will have these blues and greens at different place. And so the decision boundary will change. So there is very high sort of a variance of the decision boundary. As you keep taking different samples, your answer keeps changing. It's a classic example of, what is it a classic example of? It's of example of
Variance.
Variance, high variance.
High variance.
The high variance or overfitting. This k is equal to 1 is listening too much to the data. Right? It's very, very overfit solution. So that is the journey from overfitting to underfitting at the other extreme. So now one way that you could remedy this is you can bring the kernel to the rescue. You use a distance kernel. Let's bring in the concept of a distance kernel. So remember, what is the notion of distance? Distance between 2 points is what? It is anything that follows these properties. Dx x prime is equal to 0 if and only if x is equal to x prime. X and x prime are the same. And just recapitulating what we said is the definition of distance. And furthermore, we said that there's a triangular inequality dx to some other point. So you take a detour plus d, obviously, let me put this as vectors in some space or something like that. Dz to dx prime will always be more than or equal to the distance from, direct distance from x prime. So in very practical terms, when you go to work, quite often your journey to your desk always involves a z, which may be the coffee machine, the water cooler, or something like that. But your journey home is always a straight journey back, and which feels shorter. Obviously, the journey back. Anyway, I'm joking. So this defines the concept of distance. Typical distances that we talked about are the Minkowski distance, and just as a recap, what we talked about as the distance was that there is the norm, the dn of x between x and x prime, right? So let us define x, delta x is equal to x minus x prime, right? And the mod of this to be this, absolute difference. So by definition, the Minkowski norm of n is equal to n1 to infinity is defined as delta x I. So the component wise, you could look at the component delta xi is I, the ith component, right? So the component wise delta xi to the power n summed over all of them. In other words, it is delta x1 n plus delta x2 n, and the whole thing summation over I, and the whole thing to the power 1 over n. You have to take the nth root of it. 1 over, sorry, this is n should be here, nth power, and 1 nth. You remember that d is equal to 1, if you recapitulate, was the, what kind of a distance was it? Manhattan distance.
L1 or Manhattan, yeah.
Yeah, n is equal to 1, sorry. The n is equal to 1. And people often use the word L. So let me use the L. L is equal to 1. L, depending upon which community of crowd you come from. But machine learning crowd people tend to use the word L. L norm. The word people use is L norm. When they do that, they always are referring to the Minkowski distance. This is your Euclidean distance. Your Euclidean distance, and go ahead. So one thing is, I'll give you an intuition of how it looks in space. Take a unit. What does a circle look like in Euclidean distance? L is equal to 2. Actually, let me just put it here. L is equal to 2 is here. L is equal to 2 is what? You realize that if you make all points, so let us have a definition of a circle. Circle is defined as all points, and let me call it the unit circle so that I don't have to worry about radius. Radius is 1. All points at unit distance from origin. So this is the definition, right? We will define the circle as that. Anybody would like to argue with that definition? Is that self-evident? That's how we define circles?
Yes.
Yeah. So now let's think what happens when we do it for L is equal to 1, the 1 norm. So points which are at the same distance are here. But the surprising thing is, because we say that delta x, so x, there's no x1 norm, x norm 1 plus x2 norm is equal to 1. What does this equation look like? This is the equation of a straight line. It actually looks like this. And let me give you the intuition. See, you can go unit distance in this direction, right? Or you can go unit distance in this direction. Or you can do this way. You can go halfway here and halfway up. Or you could go 3/4 way up here and 1/4 way up. Or you could go 1/4 way and you could go 3/4 way up. But ultimately, if you are a taxi driver with only, let's say, that gas in your tank for 1 unit distance, this is pretty much the envelope of how far you'll travel. Do we see this, guys?
Yes.
Yes. So we say that a circle for L1 norm is actually diamond shaped. It's not round, it's diamond shaped. Do you see this diamond shaped circle? Right? This is how it is. And that raises a very interesting issue. Oh, well, the first time you see this, you're a bit surprised, right? Because our fundamental notion of a circle has always been round, doesn't it? But in a different norm, the circle looks differently. In fact, what happens is if you go to L is equal to half, it will become like this, much more pointy. And we will need this intuition when we do regularization. It will begin to look like that. On the other hand, if you do, so this is L is equal, let me put the word here, L is equal to 1. This is L is equal to 2. What does L is equal to 3 and so forth look like? So remember that we had a unit circle for L is equal to 2. The L is equal to 3 will develop a little bit of a bulge over this. Will look like this. Are we together? It's bulged out a little bit. This is L is equal to 3. And then when you remember, we talked of the infinite norm. L is equal to infinity, right? And that devolved to the largest value, the largest delta x max, right? So that looks in this triangle, looks like this. So it looks actually like a unit square, actually. The circle devolves into unit square. Let me explain why that is so. So
what is L exactly?
The L is, see, we talked about the L norm. Right? The L is this, L to the power L. So let me recap this, what L is. So recap. L in Minkowski norm. Minkowski's definition of a distance, Minkowski norm. It is called the norm. What it means is, look at this expression. The Lth norm of a between 2 points, distance between 2 points is defined. It's a generalization of Euclidean distance. It is defined as this. You take the x1 minus x1 prime absolute value to the power L plus x2 minus x2 prime to the absolute value L, and you keep doing on, but let's stick to 2 dimensions, and to the 1 by L, the square root, the Lth square root of this, where L can take values from 1, 2, 3, all the way to infinity. So
Dimension?
Now, come again?
Like L is dimension?
No, L is not dimension. L is the measure. It's a way of measuring distance. That's why it's called norm. Your data may be in 2 dimensions, but you may still take the infinite norm. In fact, let's look at 2 dimensions. So if you look at it, L is equal to D2. What does it become? D2 x prime is our familiar Euclidean distance, x1 minus x1 prime square plus x2 minus x2 prime square root. Right? Now you realize that for even powers, you don't even need the mod. So this is nothing but x1 minus x1 prime square plus x2 minus x2 prime square. This you remember from your basic high school pre-calculus or algebra. What is this? This is the Euclidean.
Yeah.
This is your Euclidean distance. Now D1, the first norm of x and x prime is equal to, the same expression becomes x1 minus x1 prime mod plus x2 minus x2 prime mod. That's it. And because there's the 1th root of a number is 1 itself, right? What does this look like? This looks like your Manhattan distance or the taxi driver's distance. Right? The idea being that in Manhattan, cities are on a grid. So you can only go along this direction. Right. So this was from a previous lecture. So I would say it may be helpful to watch the video of the last lecture, which I just haven't posted. The YouTube recording is there. The live recordings are there. You should do that. And I'll put a cleaned up version also. But it's all there, guys. Are you aware that all the lectures, like including this one, it is being live broadcast on YouTube? You can actually watch this entire class sitting comfortably on your sofa and watching it on your television. Okay? And not only that, after live, those recordings stay public. All the class recordings are at this moment public and present on the YouTube support vector site. If you haven't gone there, please go there, subscribe to it, watch those videos, and you will get that. So this is a recap of what we did before. So this was, who was asking this question? Sonal, was that you? Who, or Kamya? Who was,
L?
yeah, sorry, who was asking this question about the L? Yes?
Yeah, that was me.
Me as in?
Sonal?
Sonal, okay, good. So Sonal, did you understand this idea now?
Yeah, I did.
So this is, so now the peculiar thing is, see, what mathematicians do is they take intuition from real life and then they abstract it, they make it more general. They go beyond that, try to go beyond that, right? So that is what we are trying to do. Oh,
so this is basically just a different distance formula, right?
This is indeed just a different distance formula. And guys, 1 second, the recording somehow got paused. Has the recording paused? I don't know. I'll just pause and start it again. Okay, so this is just another distance function. That's absolutely correct. So mathematicians keep generalizing from simple terms. So then it leads to beautiful consequences. For example, the d is equal to 2 we are familiar with. It's a nice round circle. That's a practical day-to-day intuition. D is equal to 1. This is, sorry, not D. L is equal to 2. The second norm is familiar, Euclidean. The L is equal to 1 takes a bit of a surprise, but then if you think of taxi drivers in Manhattan, they can, so suppose they have to go unit distance. They can go unit distance here, or they can go 3/4 of the way and 1/4 of the way up, or they can go half distance here and half distance here, or they could just go along this axis, all 4 units, right? So if you look at their unit distances, they will form a diamond shape or rhombus shape. Right? So, okay, so sorry, this picture I already drew. It will form this shape, right? And if you, this is L is equal to 1, and if you can even go to fractional values of L, and when you do that, you will begin to look this like this beautiful shape. So you realize that a circle in different norms looks, let's say, 1/2, looks like this. At the other end, if you keep on doing it, do you notice that it's beginning to bulge? The bulge increases. This straightens out, it begins to develop a bulge. And at the other end of this extreme, it becomes this square. How does it become a square? Think about this point. When you are here, well, the distance is, of course, equal to here. What about here? When you are here, like, what is your distance at this particular moment? You will realize after some time that this point is at unit distance, because this distance, the y distance is to be, the x2 distance is to be ignored. The L is equal to infinity just looks at the bigger of the 2 distances. So which is the bigger of the 2 here? This distance. So it is still this, till you reach this point, at which point now you are equidistant. Both these 2 distances along this are the same. And after that, it is the distance along this. So the unit circle becomes a square. It will take you a moment to think it through. So this is the Minkowski norm. Well, why are we bringing this? We'll use Minkowski norm a lot in machine learning. But here we'll use it in using something interesting. Just keep this thing in your mind. Don't worry about it. And now, distance, let's bring it to our k nearest neighbors. Oh, it's k nearest neighbor. By the way, do understand Minkowski norm because we'll need it in regularization. Today I was going to do regularization. It's 10. I want to let you go in another half an hour. But so we'll keep the topic for next time, actually, or for an extra session. By the way, I'm ready to give you guys an extra session on on boosting, right? So maybe we will need 2 extra sessions in this workshop to finish off things. But all right, let's look at this. K nearest neighbors. So you realize that suppose you have neighbors which are far off. Look at this. Where are we? Where is our intuition? Yeah, look at this. If you look at this problem, you agree that the further going far, a little bit makes sense. You know, taking 3 neighbors, 4 neighbors makes sense. But if you go too far, you again begin to lose it, because far off neighbors are not representative of the local situation, isn't it? If you take a k is equal to 200, all you get are ducks, isn't it? So the question is, can we bring some intuition to improve upon it? So one intuition that you can bring is to say, hey, you know what? People who are my close neighbors are more representative of me than neighbors which are far off. Are we together? So you can say that somebody who lives on my street, give that person twice the weightage compared to the guy who lives in the next city, when you want to know something about you. Does that intuition make sense, guys?
Yes.
Yes. So something like your attention model, right?
Oh, yes, yes. It's like that, but don't bring that here at this moment.
Okay.
So, so at this moment, so simple intuition that the further off you go, the less those neighbors are representative of you. So what should we do? It's okay to go to those neighbors, but we just need to weigh it in. We have to take a weighted average. Let's say that we are taking the vote. You take their votes a bit less value than the votes of the people immediately to you, right? Or if you're doing a regression, you're taking the average, take a weighted average. Then weigh it by neighbor. So suppose you have 3 neighbors, W1, X1, whatever the value for this is, right? Let's say that the value, the Y1, actually the value, let's say that you're trying to predict Y hat, and based on the average of 3 points, X, and there are 3 neighbors to Y2, Y1's value, Y2 values, Y3 value. Does this make sense, guys? Suppose you're trying to find the weight of a duck. You look at 3 neighboring ducks and see their weights. Those are the, well, weight is not the thing. Well, something, okay. Whatever it is, you want to find the weight based on the size, right? So you take 3 neighbors and three ducks nearby, and you take the average of the weight. Does that make sense? But the thing is, you weigh the nearest neighbor more. Let's say that the nearest is 1, farthest is 3. So for example, you could say, let me weigh this 4 times, let me weigh this 2 times, and let me far off guy, let me weigh it once, right? Distribute the weight a little bit so that the value that I come to, and then of course divide the total weight by 7. Yeah, so a 4/7, 2/7, and 1/7, right? Is the weight that you associate with each of these readings. So then what do you get? You get a weight that is more representative of this than this. Are we making sense, guys?
Yeah.
But at the same time, you're not only looking at this guy's weight, you're looking at other people's weight also. So when you do that, what you're doing is you're doing a distance aware or distance weighed nearest neighbor, k nearest neighbor. And you may still take k nearest neighbor. K is still there, how many neighbors you take. But one thing you realize that suppose you take k as very big, k is equal to 50, but your 50th neighbor is very far away. What will be the coefficient here? It will probably be 0.001, something very small value. Huh? The idea is that you make the far off neighbors very small, their influence very small, so that they don't have as much vote as the first guy, right? So what you do is, the intuition is that you take the votes or the weights, or whether it's regression or this thing, and you create a weightage function, a weight function. Actually, you call it the kernel. So actually, that also has a k value. So I won't use the k. Let me use the word weight, right? A weight that is a function of a distance between 2 points, WD, or more formally, it's a function of W, distance between 2 points, Xn. Distance of a point to all of its neighbors, DI. It goes like this. Some decay function you need, something that decreases. It may decrease like this, It may decrease like this. It may decrease like this. Do you realize that each of these will serve the purpose, right? You just say that the further off you are, the distance is, the less the weight you will give to that point in making a decision about cows and ducks or taking the weight of that animal or so forth. Is this intuition clear, guys? You need a distance, any function which fulfills the criteria, it is monotonically decreasing with distance. Right? It's decreasing with distance. It cannot just go increase, like this function will not do. This is not a good weight function. This is meaningless, right? Yeah, emphasize, like it goes up and down, etc. It won't do. So we won't do that. Actually, let me just put it here. And this is not. You need something that decreases. It may not even decrease, or it may decrease very slowly, or it may not decrease at all. It may just remain. So if you notice that if the weight doesn't decrease at all with distance, it is your K nearest neighbor without a kernel, without a distance awareness. Do you realize that, guys? Huh? That the standard KNN is nothing but, in this terminology, distance awareness, in which the weight function is constant. Is this intuition making sense, guys?
Yes.
It's straightforward, right? But you want something better than that. So sometimes people even use a step function. They say that if you are within a certain distance, I will consider you uniformly. After that, I won't consider you. So what happened is that soon people began to ask, these weights were called, Ws are called distance kernels. And it's the same idea of the kernel. So I won't go into more mathematics. So the thing is, so long as it is any function that decreases monotonically, or at least decreases, never increases at all monotonically, is a valid distance function. So there was an effort to find all sorts of distance functions. What is a good distance function? What is a good kernel? And there was a cottage industry trying to prove that this kernel is better than that kernel is better than that. And so there are many kernels that people began to use. Anything could do, a sine wave, you know, what is it? The cosine goes like this. That is a perfectly good, again, it is decreasing. It will do. You could use anything that you want that decreases. You could use a bell curve. This too is a good kernel, right? So people came up with a lot of kernels, and they began to investigate which kernel is better than the other. At the end of the day, they found out, actually, surprisingly, that the choice of kernel doesn't matter much. It does matter a little bit. But in most situations, changing from one kernel to another gives you a tiny bit of improvement in your classification or regression. It doesn't make a tremendous difference. So at this point, what I'll do is let me just move on to the other computer, and I'll show you examples from the notes. By the way, those notes I'll give you of what I mean in this context. Give me a moment. So where am I? Let me share this screen now. Share my desktop. This is it. Let's open my what is happening here? Open in the terminal. Okay, my system is not exactly behaving very well. CMD, yes. Sudo desktop, okay. Much better. So distance weight Kernel. So I'll give you guys this chapter. No, it's from this chapter. How do I minimize this? Okay. So guys, look at this. Are you all able to see my screen?
Yeah.
So suppose we are writing a classifier that distinguishes between the blue point and the, what color would we call it? Orange points? Orange points? Is that close? Orange points here. Let me zoom in a little bit and go to a single view, single page view. Get page now. View mode, single page. Okay, guys. So are you able to see this picture clearly?
Yeah.
In the picture, there's a lot of noise
Yes.
here. Points, the orange and the blue are mixed up, but still you can say that there is a separation. So we will take different values of k and see what happens. If you treat it as a simple linear regression problem, a line would just go through like this. Right? Now, what happens when you take k is equal to one nearest neighbor? Do you see how complex your decision boundary is? And I'll give you a moment to stare at it and convince yourself that it is the right decision boundary. Obviously, I did it programmatically, so it happens to be right. I wrote code to generate it. So in this situation, you have all these points and you have this k nearest neighbor decision boundary. You see all these islands and peninsulas and so forth, and this sort of backwaters and whatnot. If you look at this, if you treat blue as the sea and orange as the land, you see all sorts of geographical features. You take 5 nearest neighbor. Do you notice that the decision boundary is simplifying itself? Does this look simpler, guys?
Yeah.
Yes.
Right. Then you go to k is equal to 15, and it has simplified itself even more. You take k is equal to 100, and now it's this straight line. Or not straight line, but okay, much more smoother, much more stretched out line. Right? So do you see the variance decreasing as you increase the number of neighbors? And the question is, which is the best value of k to take? And the answer to that is whichever value gives you the best predictions on the test data, isn't it? On the validation set, whichever gives you the best predictions, that is your value of k. So proof of the pudding is in the eating. You have to validate it against data, see what the predictions are, how do they come out, and base it on that. Now, I just mentioned that we have two kinds of, I'm just taking the impact of norms. How does the Euclidean norm and the Manhattan norm affect? For the same set of points, actually, the Euclidean norm and the Manhattan norms, do you notice that they build different decision boundaries? They will break it up differently. Right? It's just something to know that you can just play with the notion of distance and change the decision boundary. One question that people ask is, hey, a k nearest neighbor, assuming that you have a notion of distance, assuming that you have the dimensionality of the problem is small and you don't have the curse of dimensionality that we talked about last time, isn't this a lovely thing? Won't it always outperform other algorithms, right?
Yeah, sodium chloride.
Yes. So I take this example of sodium chloride. Actually, it's not true because if you look at a lattice structure in an atom, in this lattices, so salt is a lattice structure. You will always get it wrong. K nearest neighbor will always come out wrong, irrespective of what value of k is, because the nearest neighbor of a sodium atom will be a chlorine atom.
Always.
And always of a chlorine would be a sodium atom. And if you take whatever k you take, you'll keep getting it wrong. Right? Again, goes to the no-free-lunch theorem that there is no way out. Nothing is perfect. Everything has its flaws. Now, when you get these norms, it will review what I just taught you about the P norm. By the way, instead of L, I've used P. Mathematicians tend to use the word P. In the data science community, we tend to use the word L, just trivial distances. But if you notice this diagram that you have here in those notes, and some of you who are repeating the class already have these notes, but do you notice how it goes from very small, like concave-like structure to convex diamond, then convex and circle, and finally to a square. That's how it behaves. Now, how do you, this distance function that you have, what is a distance function? It follows this inequality. Now, this is an example of the kernels people have. One easy kernel is just 1 over R. Simple, isn't it? Another popular kernel is just take the positive half of the bell curve. Distances are positive. This is the positive half of the bell curve. Right? By the way, what is this constant in front? It is just a normalization constant so that the integral comes to 1. This is called the parabolic kernel. It was associated with this gentleman, Ipane Chikov. I never could get the pronunciation right. My apologies to this great
Ipaniknikov.
Yeah, Ipaniknikov. Yeah. So this is this kernel. Yeah, parabolic kernel. So it's like this. A simple triangular kernel. It just goes like this, right? Well, people are creative. You can use cosine as a kernel. You can use a tricube kernel, which is this. It goes to the third power, right? Then a weighted tricube kernel. So you can see that at one point, people went crazy trying to come up with better and better kernels, right? And they thought that the actual shape of the kernel mattered a lot. Today, we know that it matters a little bit, not too much, right? And so here are all of these kernels, put here. Throw away the negative side, just look at the positive side. You see how they decay. So the bottom line is it doesn't matter much, but it does matter a little bit. So now you have two hyperparameters in your model, K, the number of nearest neighbors to take, and which kernel to pick. Generally, what happens is if you use kernels, K doesn't matter so much. The number of neighbors, it gets muted. It is not something that affects the model in a huge degree. Right? It does matter, but not too much. It doesn't matter that much. So something to remember. You tend to take rather large Ks, but let the kernel take care of them and so forth. So this is it. This is just saying whatever I said in words in a more formal language. So how do you do regression with it? Very simple. You just take the nearest neighbor and take the average of the output, average of the predictions. So you can do that. If you apply it to Hill dataset, you'll realize it makes a pretty good value. This is a lab. It is done in R. So I'll hand out the solution in R. If you apply it to the river dataset, let's see how well it does. And I have the prediction mapped out for different values of K. When you do that, you realize that it is the maximum accuracy that you get is for 8 neighbors for the river dataset. You should take 8 neighbors. So we did a search for the best model. 8 neighbors turn out to be best. By the way, if you rerun it and for different people, it is sometimes 7, sometimes 8 or something like that. So, and the accuracy is 87.3, which is what we expect. You remember that the maximum accuracy you can get is around that 89 or something like that. 90. So it's pretty good model, isn't it? The nearest neighbor algorithm, especially with the kernel. Then, how does the accuracy of the model vary with K? You can see that, in the beginning, accuracy improves as you increase K. And after that, it starts decreasing. As you take more and more neighbors, you're considering further off neighbors. And so your accuracy tends to decrease. And so your point of best accuracy is around 8. Okay? You get that. One way to simulate higher dimension, of course you can't simulate high dimension, is to take sparse samples of the data to learn. Because in high dimension data becomes sparse. So with the river data set, you could just take very few samples to learn from. And so it will simulate high dimension. When you do that, you realize that once again, the more you go to higher dimensions, the accuracy is better, the bigger the sample, the more the accuracy, which means that in lower dimensional spaces, KNN works well. In high dimensional spaces, you begin to get into trouble. There's the curse of dimensionality that we talked about. Right? So this illustrates that. The same thing for the flag data set. Right? I'll post these notes. By the way, I'll put it on the website, all of these notes. I know that Slack is getting a little disorganized. There are too many things here. I'll post it to Slack also and to this. So we have the flag data set here. Once again, the same accuracy curve that you see. It peaks around, what is the peak value here? You get a peak around K is equal to, around K to 5 to 10. In this plateau range, you get maximum accuracy of 87%. Right? The Hill dataset, what does it do? Hill dataset gets the predictions right with very high degree of accuracy, 99% R squared, coefficient of determination, the R squared, very high. So these things work. Now I gave this as a problem. Look at this problem, guys. I can give you the data if you guys want the challenge. The code to generate the data is here. You look at this data And you realize that building a regression model for this can be pretty hard, especially a linear regression model. Do you agree, guys? Because the surface is anything but linear. Do you see that, guys? Anybody?
Yes. Yes.
Yeah. It's a highly nonlinear surface. And yet, if you have rich enough data, it fulfills our criteria: low dimensions. If you have enough data points, k nearest neighbor can do extremely well. And I leave that for you as an exercise. I'll give you guys the data and give you the formula. This is basically a modified form of what is called a sinc function. I call it the flower data set. And so along with your thing, there's also the flower data set. I'll release it. And so you can try it out. You'll be surprised. KNN works, kernel KNN works like a charm, right? But it's very hard to model a parametric model, like a linear polynomial equation to this. It's a very complicated polynomial. You notice that? Looks like a flower. So, well, guys, today we had a long session. I'll end with that. We did not get to regularization. I will consider whether to do it in an extra session or to do it next week. Right? We have one theory session left. We can choose regularization. We can choose a recommender system. Recommender system, actually, on second thoughts, we are going to do in the math class very deeply. So let me skip that and keep next week for regularization. This week, one of these days, I will give, this week or weekend, perhaps, the extra session, will give on boosting. Let's do it. So when would you prefer, guys? During the week or during the Saturday? Boosting.
Let's do it on Saturday.
Let's do it on Saturday. All right, let's keep it for Saturday, guys. We'll do
boosting Saturdays. Okay.
And Monday, we'll do regularization. That will be the last topic for this course. And after that, forthwith, we'll get into the math of machine learning. Right? With maybe a week of gap, we'll start. So with those words, I will end today's session. If you have questions, stay back. I'll answer those questions. Any questions, guys?
Yeah, there's another method where the number is for the number of clusters as opposed to the number of neighbors, right? The centroids.
Yes, 1 second.